Okay, continuing on with switching here. Our next section relates to Layer 2 voice and video support, specifically how we deal with trust boundaries and quality of service markings, and then additional applications and requirements that phones need. For example, power over Ethernet, which is actually our first topic here, power over Ethernet, which is required for small power devices like IP phones or access points, or in some cases, IP-connected cameras, which can be provided by the access layer switches. So the ultimate goal here is that running PoE, it reduces the amount of cable pulls. So when you run a regular Cat5 cable or Cat6 or Cat6e cable, and you're installing an access point, or you're going down to your phones at the desktop level, you don't necessarily need to pull additional power in order for those devices to connect to the network. It also gives us some centralized management for power. There's some kind of neat things that you can do with power over Ethernet, like setting up scripts that after office hours, your phones or your access points automatically power down to try to save on the overall energy usage for the network. So PoE compliant switches, these are going to be supported over twisted pair, so it's not going to be over optical interface. It must be over copper. For switches that do not support this, you can get external power injectors, in which case the cable runs from the switch to the injector, then from the injector down to the phone or to the access point. It would again give us a centralized management of the power. Now, implementation-wise, there's two ways that PoE works. We have a Cisco pre-standard way, and then the new IEEE standard, which is defined as 802.1af. Now, most newer Catalyst switches will support both of them. Really depends on which particular device, or it depends on the device which particular standard they want, whether they want the pre-standard or the IEEE version. So the PoE detection process of the switch will automatically figure out exactly what the particular device wants. So if it's an older access point, maybe it wants the pre-standard, or if it's a newer phone like a 7960 phone, then it uses the 802.1af. But configuration-wise, it's simply going to be one command at the interface, power inline auto, or power inline never if you do not want to run PoE. One important point about this with PoE is that every switch will have a power budget, which basically means it has a maximum amount of power output that can be as an aggregate amongst all ports. So if you have a 48-port switch, it's unlikely that the switch is going to be able to do PoE on all 48 ports simultaneously. So you do want to take this into your design considerations when you are doing, or when you're choosing platforms and when you're doing your capacity planning. It's more than just bandwidth requirements. It also could technically be the power requirements as well. Now, beyond the physical layer requirements of the powering, the next big thing we need to take a look at in Layer 2, as it compares to either voice or video, is how the quality of service or QoS requirements differ from real-time traffic flows like voice and video as compared to flows like FTP or web browsing or email, where the user is not really looking at the application to respond on a real-time basis. Now, voice traffic typically does not need a lot of bandwidth in the network, but it does have a strict requirement on round-trip time, or the RTT. Basically means the amount of time that it takes for when you transmit your voice for it to get all the way to the other end, and then for packets to return. So think of this like a ping. A ping time, ping latency would be a round-trip time measurement. Okay, the next would be the jitter, which is the variation in delay. So if the first couple packets you're sending have 20 millisecond delay, then the next few packets have 100 milliseconds, and then back to 20 milliseconds. Voice typically does not deal well with this type of variation in the delay. So the result of jitter is that most of the time you will not be able to understand what the person on the other end of the phone is saying, and then you'll have to ask them to retransmit just to say what they were speaking about again. Also, voice does have a requirement of packet loss. Since voice calls and video conferencing usually use UDP, which is not a connection-oriented protocol. It does not support retransmission. Most of the time for voice and video, it does not make sense that retransmission would be implemented. Because by the time my voice gets to you right now, if a packet is lost, it doesn't make sense that that packet should come in 500 milliseconds later out of your speakers. Okay, so same type of application like we're using now. This is UDP-based voice over IP. So if there's a bunch of packet loss in the transit path, then you're not going to be able to hear what I'm saying over the application. So it's always these three that you need to keep in mind. The round trip time, which is going to be the delay, the jitter, which is the variation in delay, and then the packet loss, which is basically the reliability of the end-to-end circuit. Now, the reason that we run into these problems with voice over IP as compared to the legacy TDM networks or the POTS network, the analog telephone network, is that the legacy networks used what is known as time division multiplexing, or TDM, whereas packet networks are statistically multiplexed, which means that oversubscription can happen. Or in other words, there's not enough bandwidth in the network to meet all the needs of the user applications. So usually when you're web browsing or you're doing email or you're doing an FTP transfer, it's up to the application of TCP just to deal with the problem of the oversubscription. So if there's packet loss, TCP knows how to do retransmission. It knows how to do the sliding windowing to automatically have flow control built into the session. But with voice over IP, we need to make sure that the network is properly engineered so that the voice calls do not get dropped. Okay, this is where we are going to deploy, from our point of view, manual quality of service mechanisms to make sure that the voice and the voice calls and that the video conferencing gets treated differently by the network on a hop-by-hop basis. Make sure that we meet those strict requirements. So it may be that the end-to-end delay be no more than 80 milliseconds and that we have less than X amount percentage of packet loss and jitter. It would be based on the actual application itself, what the requirements are going to be. Now, in today's networks for voice and video, the way that we are going to implement this is with a system that is known as the Differentiated Services QoS model, or the DiffServ QoS. Now, what DiffServ QoS means is that instead of looking at traffic on a flow basis, meaning looking at the end-to-end traffic pattern and treating all traffic flows equally, where a flow could be a voice call or a flow could be a web browsing session or an FTP session, we want to differentiate, or just tell the difference, between the voice and the data traffic. Now, what is nice about the DiffServ model is that it is very scalable. This would be as opposed to the legacy implementation, which is known as Integrated Services, or IntServ, which uses things like the RSVP protocol or Resource Reservation Protocol to try to get the network to manage all of the flows as reservations. So we're using the opposite of that, which is the DiffServ model. Now, DiffServ basically means that we need some sort of manual classification policy so that the network knows what is a voice flow versus a data flow. And we're going to do these based on different types of packet markings. Now, packet markings can exist in the layer 2 header, like an Ethernet class of service, or in ATM, or in MPLS, the experimental bits. It's going to be based on whatever particular media that we are dealing with. Now, from our point of view from the LAN, this is going to be in the layer 2 Ethernet header. Could also be some sort of higher level classification, like a layer 3 IP precedence, or layer 3 DSCP, which is the Differentiated Services Code Point Value, DSCP. But the key factor with the DiffServ model is that we need to make sure that the entire network agrees on what these QoS markings are and how they should be processed. And this is what our implementation from a layer 2 point of view is mainly going to center around. To make sure that the layer 3 markings, or the markings, however they're done, whether they're layer 2 or layer 3, as traffic enters the layer 2 domain, so as it enters the layer 2 Ethernet switches, we need to make sure that they are enforcing the markings based on the QoS policies that we have set up in the rest of the layer 3 network. So in a typical end-to-end QoS design, the switches at the access layer are in charge of doing the marking. They're in charge of doing the classification. Once the traffic gets to the routers, the router queues the traffic or does some sort of management as the traffic flow is going out to the rest of the network based on the classification that happened at layer 2. But anytime we run into a situation where the marking does not agree with what the policy is defined as, then the entire end-to-end QoS model is going to fall apart. So it's our job at layer 2 to make sure that the markings are consistent with however we define the QoS policy. Now the marking itself, how it's done, is going to be arbitrary. It's up to us as we are defining the end-to-end QoS model. Are we going to use layer 2 classification? Are we going to use layer 3? Or could even be something higher level based on like a TCP or UDP port. Most of the time in layer 2 networking and then into the layer 3 router QoS, it's going to be based on these values here, either IP precedence or DSCP. There's some well-known codes for IP precedence or DSCP that are generally used to represent our real-time flows versus the flows that do not need the preferential service. So a real-time flow would be like our IP telephony call or video conferencing versus a non-real-time application like email, SMTP, or POP3 email. Now, we'll also see a little bit later on the routers, when we get into our routing topics, that we could do classification based on different traffic characteristics. This would also be where the feature called NBAR, or a network-based application recognition, comes in, where we could classify things based on the application signature. So this is where you would manage like how your peer-to-peer file sharing applications are dealt with. So how do you do policing on to BitTorrent or to Kazaa traffic in the network? You do that based on the characteristic, which would be the application signature. Now, from a layer 2 point of view, usually that's going to be too far of a classification for the access layer switches to have to deal with. So when we look at like the Catalyst 3550s or the 3750s, traditionally the switches that we would consider as access layer, they're not going to have the capabilities to do deep packet inspection and really to look for the application level or the application layer. So we're mainly going to constrain our work either to layer 2 or to layer 3. Now with the markings, their actual encodings, the layer 2 marking for Ethernet is what we call the class of service, or the COS. Okay, the COS bits are only included inside a layer 2 trunking encapsulation. The layer 2 markings would only be in an ISL trunk or an 802.1q trunk. Okay, this is why there's going to be limited application for this. On a regular access port, there's not going to be layer 2 class of service. For the layer 3 markings, this is going to be pretty much in every single IP packet. You could do the marking. So there's a field in the layer 3 header that is known as the TOS, the type of service. This is where we encode the differentiated services code point, the DSCP, or the IP precedence, the IPP. Now, normally you would want to make sure that these markings match up so that we don't have any inconsistencies when we're doing the classification policy. So really there's no rules as to how they should work, but for the example here it says class of service 5 with IP precedence 0 is not illegal, but it makes little sense. Okay, normally you would say class of service 5 equals IP precedence 5 so that you're maintaining the marking end to end and there's no confusion about what the classification policy is designed to do. Okay, class of service 5 is normally what you would use for your phone calls or your real-time applications. Same with IP precedence 5. IP precedence 5 is known as critical. That would be for your real-time flows. Now, once the classification has occurred, so we figured out based on either the layer 2 markings or the layer 3 markings what the traffic is, we apply the QoS in what is known as the per hop behavior, or the PHB. Okay, the PHB is when we're actually implementing our quality of service tools, things like queuing or policing or traffic shaping or prioritization, in order to actually deal with the traffic. Now, at this point, we're not going to get into QoS implementation very much because there's very little that we can do at the layer 2 switches versus the layer 3 routers. But from the layer 3 routing point of view, definitely this is something that you do want to understand. Okay, so we'll talk about that later when we get into our routing and then to the troubleshooting topics. Now, the per hop behavior generally is going to fall into 3 categories. We have assured forwarding, expedited forwarding, and then best effort. Okay, assured forwarding means that we're going to guarantee some sort of bandwidth, but it's not necessarily the best type of traffic in the network. Okay, typically this is where you would say that maybe my POP3 mail is guaranteed 1 megabit per second across the link, or my web traffic that's going to an internal server, or it could be something like IMAP or whatever typically applications that are bandwidth hungry, but they really don't need any strict type of latency requirements. So typically these are going to be TCP-based applications. Now, expedited forwarding, or what we define as EF, needs priority treatment. This is typically going to be like your voice over IP calls or your video conferencing. Okay, there's going to be some different types of QoS mechanisms that we would employ to give assured forwarding, which is a reservation of bandwidth, versus the expedited forwarding, which is the priority treatment. Okay, the priority treatment is also known as an LLQ, which is a low latency queue. Basically means that as we are processing the traffic, we're trying to give it the minimum amount of delay as it's sitting in the buffers of the device waiting to be sent. So when the router or switch receives the packet in, there is going to be some sort of finite time that it takes to receive the packet, to process it, move it between interfaces, and then actually dequeue it on the outbound interface. So low latency queuing, the idea here is that we want to take the minimum time possible from when the packet is received to when it actually leaves the outbound interface, because it's some sort of application that's very sensitive to delay and jitter. Last but not least, we have best effort forwarding, which is no guarantee. This is also what is defined as the scavenger class. So scavenger class would be things like your maybe YouTube videos or BitTorrent in your production environment, where you're not necessarily limiting it, but you're not giving it any type of guarantee. So if nobody else is using the network, you can download really fast from BitTorrent, but if people are making phone calls, want to make sure that that is first in line as opposed to the best effort, to the scavenger class. So implementation-wise, we'll talk about that later, specifically how we do this with things like the modular quality of service on the router's command line. Okay, so up to this point, from a layer 2 switching point of view, the key is that we need to make sure that the classification and marking policy is correct, because once the traffic flows get to the routers need to know how to deal with the different flows. So the router needs to know, is this supposed to be assured forwarding? Is it supposed to be expedited forwarding? Or is it supposed to be best effort? One way we can do this from a layer 2 point of view is by defining different types of trust boundaries. Now, trust boundaries are used to either permit or deny whatever classification the traffic already has as it enters the network. So we're basically relying on the end application, like the IP phone itself, to tell us, is this supposed to be expedited forwarding, or is this supposed to be assured forwarding, or scavenger class traffic. So this configuration of the trust boundary, normally this is going to happen on the network edge, like on the access layer switches down to the phones or down to the end hosts. Now, untrusted ports are going to have their markings reset to 0, which means that they're going to fall back into the best effort. So usually any type of marking that is 0, whether this be a class of service 0, an IP precedence of 0, or a DSCP of 0, this would be the worst type marking in the network. So it doesn't necessarily mean that that traffic is going to be punished. It just is not going to be guaranteed low delay or low latency like we would want the the voice type traffic be defined or to be serviced as. So visually, from the access layer point of view, the trust boundary is going to be on these ports that are connecting to the end applications. So the IP phone itself is going to send the traffic in, and it's going to tell us what is the difference between the actual voice over IP call versus maybe web browsing that someone is doing on their desktop behind the phone. Okay, we'll see the phones themselves are able to deal with this by making a differentiation for us from what the traffic is coming in on their extension versus the actual phone traffic itself. Now, sometimes it's a little bit more difficult. As we see here on the bottom right, we have a laptop that's running something like Cisco's IP communicator, where the phone application is on the laptop itself or on the desktop. In that case, it gets a little bit more difficult to differentiate between what is the expedited forwarding traffic, like the voice phone call, versus the other applications that are on the device. So in the end, it's really up to us to define what type of traffic is trusted, what type of traffic is not trusted, and then if it is not trusted, what type of marking is it going to be receiving. So ideally, we want to configure the trust boundary basically on every single port of the access layer. So then when the traffic gets up into distribution or to the router where we're actually enforcing our QoS, the router doesn't have to worry about doing any marking for the traffic coming inbound. So we would be assuming here and here that the traffic is already properly classified. Okay, there's a question here. Can you extend the trust boundary down to the IP phone, which is a switch? Yes, you can. Okay, and actually that's the last bullet point I have here. Okay, what you can do, if we look back at this diagram, from this switch, let's say this is switch 1, you could tell it to trust the voice that is coming in from the phone. Let's say that we give this a marking of 5, class of service 5, or IP precedence 5, but at the same time, the traffic that's coming from the PC, set this to 0. So the phone will be able to tell the switch what is the difference between the data traffic and the voice traffic. Okay, we'll get to that in a second. It has to do with the basically a .1q encapsulation that the phone is adding onto the Ethernet frames. So configuration-wise in iOS, the trust state is going to be at the port level with the command mlsqos trust. Now we can define the trust based on the class of service, the IP precedence, or the DSCP. Which one you choose really depends on the application. So you need to know what are the individual models of phones, or what is the application that's running on the end host, and what type of markings are they sending. So for example, a video conferencing application may be sending traffic that is marked as DSCP-EF, which is for the high priority expedited forwarding. So in that case, we would want to tell the port to trust the traffic based on the DSCP. Where with IP telephony, at least with the Cisco phones, most of the time you can just trust the class of service because the phone itself will mark its phone call as class of service 5. Okay, there's also an option where we can do a conditional trust based on the Cisco Discovery Protocol, or CDP, which basically means that if you have a wall jack in your network and you have the possibility of a phone being plugged in or some other device being plugged in, let's say it's a laptop or it's a phone, but it's not both at the same time, the switch can figure out when the phone is connected and trust the port in that case, and then when the phone is not connected, not trust it in that case. So since the Cisco phones are already running CDP, the switch just says, listen for the phone through CDP. If you see it, trust the port. If you don't see the phone CDP coming in, then do not trust the port. So if the network is very dynamic, then this would be a good choice there to do it based on the CDP. But of course, if you're using IP telephony from a different vendor, then this is not going to be supported because CDP is Cisco proprietary. Now, for cases where the phone's port goes from the switch to the phone and then to a device behind it, like your desktop or laptop, This is where we use the command switch port priority extend. So we're telling the phone what marking do we want to receive from the extension. So usually this would be like to remark it with a class of service 0. This gives us the result that I was drawing out here on the diagram, where the PC's traffic, their web browsing or their email, is going to be marked as 0, but the phone call is marked as 5, and the phone call gets marked as the high priority. So in any case, from the access level switch, we're not really doing anything with the traffic. We're just making sure that it's marked in the correct category. So once it gets up to the routers, then the routers will know how to treat it as it goes out the links. Because most of the time, if we consider that these are 100 megabit per second links, or even gigabit uplinks, or possibly gigabit ether channels, most of the time voice over IP does not have trouble in the LAN. It's when it goes over the WAN link, maybe this is a multiple bonded T1s, or maybe it's a T3 link. This is typically where the delay is going to be incurred. So as long as traffic is marked properly up to the router, then the router is going to have some sort of queuing mechanism to deal with the traffic properly. So next we need to know, how does the switch actually know that there's a difference between the voice phone calls going down to the phones and the data traffic that is going behind them? Okay, we need to make sure that these are categorized separately because they have different transport requirements, which would be the QoS, and then possibly different security requirements. So we may want an access list that corresponds to the data traffic, but we're not really worried about somebody hacking into our phone and then using a different call manager server. So we're going to treat them as two different types of flows. Okay, the easiest way to do this is to separate the traffic into two separate VLANs. So technically, when we are running IP telephony and we have the port connected from the switch to the phone to a PC, so it's still one port on the switch, the port is going to be running as a limited .1Q trunk. So there's going to be the normal data VLAN that goes to the PC, and then the voice VLAN or the auxiliary VLAN that is used for the phone call. And this is going to be sent from the switch down to the phone with CDP. So a couple different examples here. If we were to say switch port access VLAN 20, switch port voice VLAN 10, this tells the phone to mark its packets with a .1Q header of 10 as they're received inbound. So anything that is not received with 10, we're assuming it's part of the access VLAN. Now, there's a couple different ways that we can do this, different markings. The first one here is probably the most popular. This one is the most straightforward. So it really depends on how old the implementation is and what particular equipment you're using. But these are the 4 different variants. Okay, also, like I mentioned, since the devices are sharing the same physical port on the switch, using the .1Q trunk allows the phone to encode the class of service of the traffic. Because the class of service field in the layer 2 header, it only exists inside the .1Q trunk and the ISL trunk. So there is no QoS field, there's no class of service field inside the normal Ethernet header. It's only inside the trunking header. Now, another variation we have for this actual implementation from the layer 2 switches is a feature that is known as auto QoS, or layer 2 auto QoS. What this is designed to do is automate our trusting and classification policy to match up based on the particular application that we are using. And I'll show this on the command line in a second here. So it's basically going to be just one command at the interface where we specify that we're running QoS for voice, and we're connecting to the Cisco phone, which would be like a 7960, Cisco soft phone, which would be like the IP communicator, or whether we just want to trust the port because there's some other application that we're using. So let's say there's an IPTV application or video conferencing, It's not necessarily the phone or the soft phone, but we still want to trust the port. Just issuing this single command is a macro that changes a bunch of queuing options behind the scenes for us. Now, you will be able to see the result of it, so it does give you a good recommendation as to what a voice config would look like at the layer 2 switches. Okay, this question here, is this auto QoS used in the real world? It really depends on how big your implementation is. It's basically just a macro that's trying to help you with the classification. What it is useful for is to turn the feature on and see what their recommendations are. And then based on that, you can configure your own templates that you would apply down to your access layer switches. But let's say, for example, on switch 1, we have port 1 that is connected to a phone. So let's go down to port 1, and we'll say auto QoS voice over IP. Let's say that this is a phone. Now, if we look at the running configuration on the port, it says, first off, we are trusting the port based on the fact that there is a Cisco phone there. So we're looking for the CDP information coming from the phone. Okay, next it says we have a service policy input auto QoS police Cisco phone. Okay, this is referring to a modular quality of service, or MQC policy, that is affecting traffic as it is being received in on the interface. Okay, we can see what the result of this is if we say show service policy, or show policy map, excuse me. Show policy map, and then we'll say the name, auto QoS police Cisco phone. Okay, this policy says that it is made up of 2 subclasses. The 2 subclasses are auto QoS voice over IP RTP trust, which is the real-time protocol. And real-time protocol is what the actual phone call data is made up of. So the actual voice traffic is, it's an IP packet. Inside IP, it's a UDP packet. And then it's a sub-encapsulation known as real-time protocol, RTP. Okay, then the second class, it says we have auto QoS voice over IP control. So the control traffic, this would be the negotiation from the phone to the call manager for actually doing the call setup. So these 2 different types of traffic, that would get different service agreements in the network. Usually the control plane of the phone needs to be guaranteed bandwidth. So although it be just a very little amount of bandwidth, we need to make sure that's guaranteed. But the actual RTP, the real-time protocol, this needs to be guaranteed priority. Okay, next thing we would want to look at here is what are these classes actually defining. So we'll say show class map, auto QoS VoIP RTP trust, and I could just say actually just show class map. Then we have the control trust. So it says the RTP, it's matching IP DSCP EF for expedited forwarding. Now the phone itself, the Cisco phone, will mark its class of service as 5, the IP precedence as 5, and the DSCP as EF, which is actually 46 in decimal. So what the switch is saying is that I'm looking for this third value coming in here. I'm looking for DSCP 46 to come in. I'm matching this, then setting it to be EF. This is actually redundant. You don't need to do that here. But we're making sure that the phone itself could not send more than 320 kilobits per second. So it's allowing somebody to make a phone call, but what it is preventing is someone pretending that their non-voice traffic is a phone call. So let's say, for example, I am on my laptop connected to the network, and I'm trying to get better service for my BitTorrent downloads. I could run some sort of marking on my laptop locally that marks all of my traffic as DSCP-EF, this would try to trick the network into giving me assured forwarding or better forwarding throughout the network. But the policy that AutoQoS has configured here is preventing that. It's saying you are limited to 32,000 bits per second on the link. If you go above that, you're going to use what's known as the policed DSCP mutation map, which is going to change the priority of the traffic. Okay, then the voice over IP control, it's doing the same type of thing. The two categories CS3 and AF31, these are what the control planes would be for the voice traffic. So that's going to be the call setup. Okay, there's a question here. Isn't 32,000 a little bit too much for voice? It really depends on the individual codec that you're using. Because it's not only the sampling rate of the codec, it's also all the additional overhead of the RTP, the UDP, and the IP. So it's a little bit outside of our scope for talking about the payload calculation for voice, but it's basically saying here at a worst case scenario, it's going to be 320K. At a best case scenario, it's going to be somewhere around 8K, but it really depends on the individual codec that the phone is using. Okay, also, if we look at the running configuration, there's some other global changes that this AutoQoS is making. This first one, it says MLS QoS map policed DSCP. What this is doing is it's saying that if someone marks their traffic as DSCP-46, which is expedited forwarding, DSCP-EF, and they exceed that policing, so they went over 320K, you're not going to drop their traffic, but you're going to remark it to 0. So we're moving it from the expedited forwarding category down to the scavenger class, down to the best effort. So it's just making sure that the marking is enforced correctly. Now this here, the MLS QoS shape round robin queuing, this is basically saying how much bandwidth is going to be allowed for different types of queues as it goes in and out the interface. So basically the only thing that we would want to know from this is that, and let me correlate this with the interface here. Long story short, those shape round robin queuing modifications, it puts your voice traffic into the priority queue. So it makes sure that when traffic goes out that port, so back down to the phone, and it's marked as DSCP-EF, it's being sent out before your other normal data traffic. So this is a fairly involved policy that the AutoQoS is doing for you. Most of the time you would not mess around with these shape round robin queues. Your default values should be fine. You only need to change these if you see that there's some degradation in your phone calls and you're getting too much delay or the jitter is unacceptable for the application. Now, if you do want to get more information about QoS, what I would recommend to look into is the QoS exam certification guide, which is the DQoS, the distributed QoS book. It's a Cisco Press book because a lot of this stuff is vendor proprietary, the QoS mechanisms. But it goes over not only the layer 2 marking here, but it spends a lot of time on how the modular quality of service works on the routers, and then what are the differences between the QoS mechanisms. Okay, there's also a document. Let me bring up Cisco's website here. If you search for the keyword quality of service QoS SRND, this is the quality of service solution reference network design guide. And basically what this is Cisco's recommendations on how you would configure all the layers in the network in order to implement an end-to-end QoS model. So it talks about specific, if I can see it in HTML format. Now let me open up the PDF itself here. So from our point of view in the end-to-end QoS model, we would be in the campus QoS design right now because we're looking at layer 2 Ethernet. So let's say we have a Catalyst 3550, and this is our edge switch. As we could use the trusted endpoint model, where you're basically relying on the application to send the correct marking in. And if we can zoom in here, we can see this would be the MLS QoS Trust DSCP. So it's saying trust the traffic as it comes in, or we could do the auto QoS, which is just what we were doing. But it's nice because it talks about it overall throughout the whole end-to-end model. Because if you do QoS just on your access level switches, your access layer switches, and then don't touch anything else, it's not really going to accomplish anything. Basically, every device in the network that is being used for transit for the traffic has to be involved in the QoS model somehow. Whether it be classification down to layer 2 like we're doing here, or whether it's the actual per hop behavior implementation, which is the queuing, the outbound queuing, and the inbound policing on the routers.